Welcome back, everybody. We're about to get started on some really fun stuff. Our topic in this lecture is deterministic finite automata, often called DFAs. And this is kind of fun, and you may find it a bit more intuitive, a bit easier than some of the other stuff we've done. We are going to spend a lot of time this semester talking about regular languages. Remember that one of the things that we're trying to do is we're trying to prove things about general computers. And it's really difficult to prove something about an all-purpose computer until you understand how to prove things about very, very simple computers. So we're going to spend a lot of time this semester talking about effectively computers that recognize regular languages, right? And we will move on to more complicated computers later on in the semester. But so far, we know how to represent a regular language as a set of strings, right? Or as a regular expression. And what we're going to do now is to get to something that maybe will feel a little bit more computer-like to you, the DFA. Okay, so let's start by just reviewing a particular regular language. Let's talk about a regular language that's over the alphabet AB, right? The set AB, those are our symbols. And we're going to call that alphabet capital A. And let's talk about one regular language that is over the alphabet capital A. And here's the regular language represented as a set, right? So if we just look at it, we've got the set that begins with the single element, the language that begins with the set containing just one element, which is two A's next to each other, right? Followed by the set containing one element, which is B starred. So if we think about that in terms of our language, that is the set of all strings that start with two A's and then have 0 or 1 B's after that. So if I ask you to find a regular expression for this language, that should be pretty easy for you to do at this point, right? So we have two A's followed by 0 or more B's. So that's just the language A, B star, right? And then I ask you, let's list some strings that are in AAB star. Well, let's see, what's in AAB star? AAB star is a set of strings. And let's try and list these in the order they appear. If we were writing it out, the language as a set of strings listing all the strings. And I've said before, when you're listing a set, you start with the smallest element and then build up. You can have another logical way to list a set if you want, but if it's an infinite set, I think that doing it based on length is probably the best way to do it, certainly for this class. So the shortest string in this language is just AA, right? The string that contains two A's and no B's. And then we've got AA and one B, AA and two B's, AA and three B's. Sorry, I'm going on to the next line. Ooh, no, not AAA, right? Two A's and four B's and so on. So, you know, those are all the strings that are in AAB. What strings are not in AAB? Well, I don't know. B by itself isn't in AAB, right? AB isn't in there. AAA isn't in there. AAA followed by a B is not in there. There's an infinite number of strings that aren't in there. And so there is a set containing a bunch of strings, all of which are not in AAB star. So here's our first example of a DFA, a deterministic finite automaton. So if you have a lot of these, it's automata with an A at the end. If you have just one, it's an automaton, O-N at the end. And let me explain to you how this works by looking at what happens with a couple of the strings that are and are not in our language, and then we will go through this a little bit more slowly and talk about what exactly is a DFA and how does it work. So you can kind of see that we have a thing that says start here, so that's where we're going to start. And then what we're going to do, let's try this example here of a string that is in our DFA, 2 A's followed by 3 B's, and let's see what happens. So we're going to go to the start, and then we're going to see that the first symbol in our string is an A, and so we are going to, from state 0, follow the A transition to state 1. Our next symbol is an A, so from state 1 we will follow the A transition to state 2. Then we see a B, so we follow the B transition and we stay at state 2. Another B, so we do that loop again. And another B, so we do that loop again. And we've come to the end of our string, right? We've used up all the symbols in our string. And once we're at the end of our string, we look at the state that we are currently located at. And if that state has a double loop, then we say, my string is in the language. And if the state doesn't have a double loop, see how these ones don't have a double circle around the states, but the 2 does? So if you ended up at a state that doesn't have a double circle, then you say, oh, it's not in my language. So since we ended at state 2, we're going to say that this string AABBB is in our language, right? Let's try another example. How about the string AA? Well, again, we always start at the start state, so we're going to start at state 0. And I can tell you that for a DFA, there's only ever going to be one start state. We see the first A, so we transition to state 1. We see the second A, so we transition to state 2. We're done our string, right? We've gone through every single symbol in our string. So now we look and we say, we ended up at a state that has a double circle, which means that I can also check off AA as being in our language. Okay? All right, let's try one of the strings that we know is not in our language. Well, that, yes, we know is not in our language. And let's see what happens when we try to look at that as an example. So let's try this AAA string. When we try the AAA string, of course, we always start at state 0 because that's where our start state is. We see the first letter A, symbol. We follow that to state 1. We see the second A. We follow that to state 2. It's looking good so far. We see the third A, and we see that we now need to transition to state 3. We've now finished going through the string letter by letter, symbol by symbol, and we say, what state am I at? I'm at state 3. State 3 doesn't have a double circle the way state 2 does, right? So that means that the string AAA is not in our language. And you can see, you know, if we try another string, for example, if we try the string just containing the symbol B, we start, we follow the B, we end up at state 3, which does not have a double circle. And so we say that B is not in our language. So now that you've seen a DFA in action, I'm guessing that you have a pretty good informal definition of a DFA over an alphabet. But let's talk a little bit more specifically. We're not totally formal yet. We can't write proofs about what I'm going to say, but we can start. So a DFA, a deterministic finite automaton, is a finite directed graph. Every single node emits one labeled edge for each symbol in the alphabet. So for example, in this example that we're doing, remember that A equals, it doesn't look very much like an alphabet, like a set symbol does it. Let's try again. A equals the set containing 2 symbols, A and B. And so that's telling me, this line is telling me that for every single node that we have here, there should be a transition outwards, right, and a labeled edge out for A and for B. And if you look, state 0 has an A transition out and a B transition out. State 1, A transition out, B transition out. State 2, A out, B out. Now notice that it can come back to where it started. That's fine, but it's got a transition that leaves. And state 3 has both an A and a B out. They happen to end up at the same place. Oh, notice, by the way, I've got this A comma B here. We talked about this when we were talking about graphs at the very beginning of the semester. A comma B here is just a shorthand for this particular edge really represents two edges. It represents two transitions. So if I have, let's get my pen back. If I have a node, here's node 3 again, this picture here is actually exactly the same as if we had one edge for A and another edge for B, right? So this A comma B is just a shorthand for saying I've got two edges in there, okay? All right, so back to our informal definition of a DFA. Finite directed graph, right? Each of these transitions are arrows. Each node emits one labeled edge for each symbol in A. One labeled edge leaves each node for each symbol. Doesn't say anything about incoming, just outgoing. The graph has exactly one special state called the start state, and that we know is just wherever the start arrow points at. The graph has a set of final states. So in the example that we have here, there's only one state, only one final state, only one state that has the double circle. But this informal definition says that we can have a set of final states. So I've got a couple of questions here. How many start states can we have? And I hope that, you're screaming, that's so obvious, Dr. K. Why are you even asking us? We can have exactly one start state. How many final states can we have? Well, because you guys are such experts at sets, I'm hoping you're saying it's so obvious, but let's think about it. How many final states can we have? The fewest number of states that are final states that we can have, well, we're told the graph has a set of final states. So we can have 0 final states, right? And we can't have an infinite number of final states, right? How do I know that? Well, sneaky, I said it's a finite directed graph. That means it has a finite number of nodes, right? But we can have anywhere from 0 up to n final states, where n is the number of nodes, right? So we could have no final states in a DFA, or every single state in our DFA could be a final state, right? And interestingly, if our, let's see, where can I write this? Here we go. If our DFA has no final states, right, then it accepts the language, the empty set, right? No final states, nothing accepted, no strings accepted. And if all of our states are final states, in other words, every single state has a double circle, then the language that we accept is A star, all of the strings over the alphabet A, right? This assumes that A is our alphabet. So let's do another example. Here's the DFA that we've been working with over the alphabet AB. And this DFA right now accepts the language AAB star. And what I'm suggesting is that we change this so it actually accepts the language AA A plus B quantity starred. So let's pause for a minute and just remind ourselves, what is this new language that we've got? So A plus B, quantity start. That means we start out with two A's, so every string has two A's. And then after that, we have 0 or more elements from the things in this parentheses, this expression, which is either A or B. So it's an AA followed by as many A's or B's as you want. In other words, any string that starts with two A's, right? So if I were writing this out as a set, I might do it like this. So my set is the set. We start out again with the shortest, which would be just AA, and then we have AAA, AAB, right? Two A's followed by an A, two A's followed by a B, and then we have two A's followed by an AA, two A's followed by an AB, two A's followed by a BA, two A's followed by a BB, and so on, right? All strings that start with two A's and then have as many A's or B's as possible. So that's what we want, right? And so if we look at our DFA here, you know, the AA transition seems to send us to state 2, which is good, right? We want to be there because state 2 is an accept state. And if you look at this DFA for a minute, I kind of call state 3, I tend to have a nickname for state 3. I'm going to call state 3 my trash state. Okay, this is Dr. K lingo. This has nothing to do with anything that the book talks about. But why do I call it a trash state? It's kind of, you know, the state that you can never get out of. The Hotel California state, maybe I should call it, right? You can never leave. If you ever make it to state 3, whatever symbol you see, you are stuck in state 3, right? Everybody see that? You see an A, you stay in state 3. You see a B, you stay in state 3. You can never leave state 3, right? So I'm just going to kind of call that my trash state. Again, that's just informal terminology that I'm using. But you can see that with our old DFA that recognizes AAB star, if we don't start out with an A, we go to the trash. If we have one A and then a B, we're in the trash. If we have two A's and anything besides B's, we have more A's, we go to the trash. So what we need to do now is we need to say, okay, what I really want is I want to start with two A's and then let myself have as many A's and B's as I want, right? So AA, that looks pretty good. This B loop looks pretty good. The trouble is we don't want to go to the trash when we see an A, right? So what we want to do is we want to get rid of that transition entirely. And what we'll do is we'll say, you know what? This transition up here, this loop, is going to loop, and that's supposed to look like an A, right? Don't know how good it looks to you. But here, let me try and draw it again a little bit bigger. I'll say B, comma, A. That looks better. So what we want to do is, once we're in state 2, we are golden. We have seen two A's, and we know if we see nothing else, we're good, we accept. If we see another A or another B or as many as we want of either of them, we're good. And so we're going to make this transition be the transition B, comma, A now, right? And so now you can see that, for example, if we look at 4 A's, we do 1, 2, 3, 4, and we end up at state 2, which accepts. If we do 3 A's and a B, A, B, we accept. But if we have a string that doesn't start with two A's, if we start with a B, we're in the trash. If we start with an A and then a B, we're in the trash. Now, I should have mentioned this earlier. I've used these terms without actually explaining them to you, but you know, when we talk about graphs, we usually talk about nodes and we talk about edges. When we talk about a DFA, we usually talk about states and transitions between the states. The truth is that, you know, if you call it a node, that's fine. I will not take points off. Don't worry, I know I'm nitpicky, but you can call it a node. If you're at a party and you want to talk to somebody about DFAs, call them states. All right, you'll sound more professional. But unless you don't want to sound professional at the party, but there you go. When you are you have a DFA and you want to have an edge on your DFA, a directed edge, you call it a transition. Again, that's just the formal name. I don't mind. You can call them nodes and edges. You can call them states and transitions. If you don't want to sound, if you want to sound smart, how's that? Then deterministic finite automaton, like I said before, is a single. And if you have many DFAs, then deterministic finite automata, right? You can still sound fancy. You know, we still sound good if you say DFAs, even though really DFA, you know, automata, ton. Yeah, okay, I'm rambling now. It's fine. Welcome to the rambling part of this class. But you get it. We use the term DFAs to represent automata, the plural, and we just say singular is a DFA. And I hope you thank me one day for all this commentary when you go to that party this weekend and you're talking about DFAs. So here's something that you may have suspected was the case. And now I'm going to tell you it is the case, but we're not going to prove it right now, okay? Which is the languages that are regular are exactly the same as the languages that are accepted by DFAs. In other words, if a language is a regular language, if you can have a regular expression for it, I promise you, you can make a DFA for it. If you have a language that has a DFA for it, I promise you, you can make a regular expression that represents the same language, okay? We're not going to prove this now, but I will tell you, in case you're interested, and maybe another trivia fact to bring out at that party this weekend, there is, in fact, an algorithm that turns a regular expression into a DFA, okay? You can turn a regular expression into a DFA. There is an algorithm that just lets you do it. Plug and chug, boom, 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 follow these steps, your regular expression will become a DFA. There is an algorithm to turn a DFA into a regular expression, and you just follow the rules and it does it. And we'll do that eventually. But for now, all I want you to know is if you have a regular language, you can definitely make a DFA out of it, or a DFA that recognizes that accepts the same language. If you have a DFA, you can definitely convert that into a regular expression. And one last thing to note, like I said, there are these algorithms, there are these algorithms, but sometimes you don't want to use the algorithm. Sometimes it's just easier to look at the DFA and turn it into a regular expression and vice versa. Okay, so let's do some examples from the textbook. So problem 2 on page 726. It says, use your wits to construct a DFA for each of the following regular expressions. Notice, by the way, it does not actually, the book should be telling us what's the alphabet for our languages, for our regular expressions, because, of course, we need an out transition for every letter of the alphabet. And there's nothing that says that these languages are not over the alphabet, say, A, B, C, D. Even though a D doesn't appear in an expression, that doesn't mean that that's not part of the alphabet. But let's just assume, since the book assumes, I'm sure, that our alphabet is just going to equal the set containing the 3 symbols A, B, and C. Okay? So let's do each of these problems in turn. Let's start with the language A plus BC. And of course, every time you see a regular expression, by now, please, please, please tell me this is completely obvious to you. And if it is not completely obvious to you, please, please, I beg you, go back, learn about regular expressions, make sure you understand them backwards and forwards, because it's just so important, right? But this regular expression, A plus BC, is the same, well, the language of this regular expression is a set that contains 2 strings, right? We've got the string with just one symbol, A, and the string BC. So this is a language that just accepts two different strings, okay? So let's try and draw a DFA for this. Let's shrink that and put it up here so we have a little bit more room. Okay, so our DFA, of course, always has a start. and then we've got our first node, right? Our first state, our first node. And you can number these however you like. I find, the book often starts at state 0. I will often start at state 0 when I'm typing it. When I'm handwriting it, I don't usually use a 0 because sometimes a 0 can look like a double circle. I mean, you can start at state 23 if you want, but we'll just start at state 1, okay? And this says, well, if I see the string just containing A, maybe I go to state 2 and I accept, okay? And if I see a B followed by a C, state 3, I'll end up state 4, and that's an accept state. And now every other string that I see is going to get rejected, right? And I need to have an out transition for every single letter of the alphabet. So let's just look at each state that we've got and see what letters are we missing. And then of course where do we send those states? Well, I'm going to send those states to, I could call it state T if I wanted to for trash. We'll call it state 5, okay? So state 5 is going to be our state where if you get here, you may not leave. So you see an A or a B or a C, you end up in state 5. So let's just go through all of the states and see if we have everything covered, right? If we have an out transition for every letter. So from state 1, we have an out transition for A, we have an out transition for B, but if the first letter we see is a C, we know the string is not in our language, so we need to go to the trash. So let's have that be our C transition. If you get to state 2, that's when you've just seen a single A, right? If you get to state 2, and then you see any other symbols, you lose. You're not going to accept anymore. So if you get to state 2 and you see any other symbols, an A or a B or a C, you're going to the trash. All right. State 3 already has an out arrow for C, but we do need another out arrow for A and B, right? And so let's just say if you see an A or a B, after you see that C, you're not going to accept. You're in the trash. And finally, if you see a B and then a C and then anything else, you're in the trash. State 4 doesn't have any out transitions right now, so we need to add some. It's getting kind of crowded in here. So what I'm going to do, there's nothing that says that there's something magic about having one trash state. So I'm just going to add another state 6. And state 6 will have A, B, and C staying at it and a non-accept state. And from state 4, if you see an A, B, or a C, you'll go to state 6. All right? And something interesting that this tells us is, for sure there's not just one way to draw a DFA, right? I mean, you could imagine that I don't actually need to have the state 6 here, right? I could have an ABC arrow from 4 up to 5, and that would be good. So let's just check again. We have a start state. Every single state has an A, B, and a C out. State 2 has A, B, C out. State 3 has A, B, and C out. State 4, A, B, C out. State 5, A, B, C out. State 6, A, B, C out. Yep, looks good. And we only accept the strings that are in our language, which happens to be the string A and the string BC. All right, so that is this problem done. All right, A plus BC. All right. By the way, I can't remember, have we seen this use your wits phrase before? I think we have, right? So we'll use our wits. Basically, it just means don't use an algorithm, don't do anything, don't do anything kind of step by step, just figure it out. Okay? So there's our DFA for the language, or for the language A, comma BC, this set, right? Or for the regular expression A plus BC. Let's do the next one. Okay, so now we need to find a DFA for the regular expression AB star plus C, right, over the alphabet ABC. And AB star plus C means there's two ways you can make legal strings in our language, right? So the language of A, B star plus C is the set that has an A followed by 0 or more B's. So A, B, A, B, B, A, B, 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 unioned with the set that just contains a C. Right? So those are our legal strings. So let's use our wits. Let's try and make a DFA for this. So as always, we're going to start by writing start, and we will make state 1. Let's take care of that C case first. If we see a C, we end up at state 2, which is an accept state. Right, because we want to accept the string C by itself. The other part of this is the AB star. So we want to accept an A by itself. So we want something like that. But we also want to accept it if it has any B's after it, but that's kind of okay. We can just have that B loop, right? And that's pretty much it, right? Everything else we want to reject, right? So let's see what we can do here. Let's make a state 4, which is going to be our trash state, right? Again, trash state is just something, it's a term that I use because I think it makes sense to me. I hope it makes sense to you. But it's not a formal part of DFAs. But from state 1, we still need to have a B, right? We've got A and C out transitions, but we don't have a B. And if you get a B at the beginning, there are no strings in my language that start with a B, so we just go straight to the trash. If you start with a C, anything that you get after that C invalidates the string. It's not in the language anymore, so let's see. This is pretty messy. I don't have a lot of space here. Of course, when you do your homeworks, you're going to do this much more neatly because you are not trying to use a stylus on an iPad with slides in the corner and all sorts of things on here. So if you're in state 2, anything that you see after that initial C sends you to the trash. It invalidates it. If you're in state 3, you can have as many B's as you want, but if you see an A or a C, A, C, it's no good. So let's just do a quick check of our DFA and make sure we have out transitions for everything, for each symbol in the alphabet on each node. So state 1 has, see, I'm using node and state interchangeably, and you should get used to that. A, B, C. State 2, everything is A, B, C on that one. State 3 has a B there and an A and a C there, and state 4 has A, B, C out. So good, we got it. So this is a DFA that recognizes the language A, B star plus C, or accepts the language A, B star plus C. Okay. Okay, so now we have a little bit more complicated language. We have A star, B, C star. A star, B, C star, plus AC. So 2 kinds of strings we can accept. We can accept just the string AC, or the string that starts with 0 or more A's and ends with 0 or more C's. Okay, now this is going to get a little bit trickier, right? Because your initial thought maybe is if you have your start state and if you see a 1, or sorry, if you see an A, you end up here for this AC part, but if you have an A, you kind of want to allow to have multiple A's in a row too, and then the B thing. But this is no good, right? Does everybody see why this is no good already? You know, this is no good, even if I put in numbers here. Because in state 1, I've got two ways to leave with an A, right? I can go to state 2 or I can stay in state 1. Not allowed, right? With a DFA, you are allowed exactly one out transition for each state. Not more than one, not fewer than one, exactly one, right? So let's try this again. Okay, so of course we need our start with state 1. And now you just kind of have to use your wits, I'm afraid. Eventually we'll get to the algorithm and then you'll be in better shape, but right now it's use your wits. So let's take care of that AC part, right? We know if we see an A and then we see a C, we want to accept that, right? And in fact, if we make a trash state here, A comma B comma C, we know that once you see A and then C, if you see anything else, you're done, right? But if you just see AC, life is good. Now let's see what else we've got. In here it says you can see 0 or more A's, right? And then a B, and then 0 or more C's. Okay. Now, one thing you might think of doing, right, initially, before you have much practice with this, is you might say, okay, I guess I should put an A loop on here so that I can represent that 0 or more A's. But if you do that, you need to be careful, because if you do that, then that allows you to have an A, 0 or more A's, and then a C, and accept that, even without a B, and that's not in my language, right? So one A and one C is in my language. Lots of A's followed by a B and then a C are in my language, but lots of A's and then a C, not in my language. So this is no good. We can't do a transition like that. Obviously, though, state 2, we have to have a way to do more than one A, right? So let's think about this. We may need to pull this apart just a little bit more. So if we start with 1A, and then maybe we see our B, right? Let's just pretend for a second that we start with 1A, and then we see a B and as many C's as we want, okay? If I start with 1A, and then I see a B, I'm kind of running out of space here, I'm sorry. So I see 1B and I'm at state 4, and then maybe I see as many C's as I want. Actually, once I'm at state 4, I think this works. What do you think? If I make state 4, that's a double circle. I hope you can see that. Then if I see an A, and then I see a B, well, I can't have 0 C's, right? So I have to accept if I just see a B. But if I see C's after that, I accept that too, right? So that looks pretty good. But what about the case where I see more than one A before my B? What do I do? Well, what you don't want to do, again, is I don't want to put an A loop on here. Because if I put an A loop on here, well, the A would come after that B, right? So that's no good. Plus, I could have A's and C's in any order, so that's also no good. So goodbye, A loop. I think what I'm going to need to do is have kind of another A path. So I'm running out of space here. So I hope you don't mind, but I'm just going to erase this. Okay. So where were we? We were trying to deal with more A's. So if I'm at state 2 and I see an A before that B, maybe what I do is I go to another state. Let's make this state, hang on, I have 2 state 4s, I just realized. So why don't we call this one state 14, because that's a perfectly valid, there's no rule that says you have to number the states in order, so that state's going to be 14. Okay, where were we? We were saying I was doing a state 5, and that's going to be an A. So now I've seen 2 A's, but I still don't accept, right, because I haven't seen my B. And what I'm going to do is I'm going to say, what if I stay here for a while with my A's? So I can have as many A's as I want now. So this takes care of the situation. If I just have 1 A and then a B, I'm good. Oh, I'm allowed 0 A's and then a B, right? So I guess I need a transition on a B up to here too, right? It looks like state 4 is kind of going to be my state where I'm good. I know that I am going for this. And in fact, I know that I'm going for the A star, B, C star situation. And I've already seen a B, right? Does everybody see that? So state 4, I can only get to state 4. I'm setting myself up so I can only get to state 4 if I have seen some A's optionally and then a B. So what I'm going to do is I'm going to do like that. All right. So if I see 0 A's and the first thing I see is a B, I get to state 4 and I can hang out with as many C's as I want. If I see 1 A, I can get to state 4 and I can hang out with as many C's as I want. If I see 2 A's, or 3, or 4, or 5, or 6, then I get a B, I'm at state C. So this looks good to me. So let's just look. So we need to have as many A's as we want, then a single B, then as many C's as we want. That gets us to state 4. And we also have the situation where we don't have any B's, but we just have a C, and that accepts. So I think now we just need to clean this up and make sure we have an out transition for everybody. So let's see. From state 1, I have an A and a B, but I don't have a C, so we'll have C go in there. That's not beautiful. I'm sorry, I really shouldn't have overlapped that. Let's fix that. I don't want to demonstrate really hideous examples here. Let's see. There we go. So that's if you see a C. If I'm at state 2, it looks like state 2 already has an exit transition for A, B, and C. State 3 has an A, B, C out. State 4 has an out for a C, but not for an A and a B. I think I'm going to make a new trash state up here, 6. That is A, comma, B, comma, C, just so it's not so messy. So if I'm at state 4, I can see as many C's as I want, but if I see an A or a B, I need to leave and go to the trash. If I'm at state 5, I have an A and a B out, but no C out. And state 6, we already have our outs, and state 14 has all its outs. So we're good. There you go. There's a DFA. Messy, but it's a DFA. I'll say it one more time. When you're doing these for homework, the first time you do it, it may look like this. You can redraw it before you submit it. Please, please redraw it before you submit it, because if I'm grading one of these, I'm going to want it to be neat. And if your peers are grading one of these, you're going to want it to be neat. Okay, here's another problem from the book. Find a regular expression that accepts the same language as this DFA. No, maybe I made this problem up. Anyway, let's see. If we look at this DFA, we just use our wits, I can see that if I see a B, everything fails, right? So if it starts with a B, it's not in my language, right? State 2 is my trash state. On the other hand, if it starts with an A, it can have whatever the heck it wants after it. So this is going to be the language of strings that start with an A, has to have an A, and then 0 or more ABs after it. So if I'm writing it as a set, it's an A, or AA, or AB, or A followed by 2 A's, A followed by AB, or A followed by BA, or A followed by BB, and so on. And as a regular expression, right, that's easy to write as a regular expression. Should be easy. If it's not, go review. That is the language that starts with an A and then has as many A's or B's as you want. So take a look at this slide, pause the video for a minute, figure out what's wrong with this. What's wrong with this? Well, your first thought is I didn't tell you the alphabet, and you're absolutely right. If I told you the alphabet was over, you know, if the alphabet's A, B, C, right, then this isn't a DFA because there's not an out transition for every letter, every symbol, but really what I was looking for on here is it's missing a start state, right? If we check, it does have an A and a B out for each BAAB, but it doesn't have a start state. So here's another DFA. No, here's another thing that is trying to be a DFA but is not actually a DFA. And it has a start state. I'm going to tell you that, let's assume it's over the alphabet ABC, but what's wrong? Pause the video, take a look. And if you look, let's see, state 2 is missing an out transition for C, and state 3 is missing an out transition for C, assuming it's over the alphabet AC. If it's over the alphabet AB, then why the heck do we have these C's in here, right? So, question, is this a DFA over the alphabet AB? If so, what does it accept? If not, why not? Pause and think about it for a minute. So, hopefully you paused, you're done pausing. When I was checking this myself, I said, well, it has a start state, it has an out transition for each of my A and B on every state. So yeah, I think this is a DFA. In terms of what does it accept, now I look and I see I don't see any double circles, right? But that's not a problem, right? Because there's nothing that says that a DFA has to accept anything, right? It says that we can have a set of accept states, and that set can be empty. So in fact, the language that this DFA accepts is the empty set, right? It doesn't accept any strings, but it is a perfectly valid DFA. Okay, here's kind of a tricky picture. Let's see if we can figure out what language this DFA accepts. So let's just kind of go through it. It looks like there's two paths to get to the accept state, right? It doesn't look like there's any trash states in here. And for the first path, you can have an A followed by as many B's as you want, and then an A, and then as many A's or B's as you want. And this path is kind of the opposite, a B with as many A's as you want, a B, and then as many A's or B's. So let's do the top path is an A, as many B's as you want, an A, and then as many A's or B's as you want. That's the top path. The bottom path, hang on, let me shrink this slightly. Writing a little bit too big. There we go. The bottom path is a B followed by 0 or more A's and a B, and then as many A's or B's as I like. And both paths are legal, so this is the union of both sets in my language, or a plus if I'm making a regular expression. So my regular expression says I can have all strings that start with an A, bunch of B's, then an A, and then whatever I want, or start with a B, bunch of A's, then a B, and then whatever I want. Okay? And what I want you to think about is just be sure that you understand why this is not the same as this language. Hang on. It's not the same as the language just A plus B star, right? It's not just any old A's and B's that you want, right? There is something going on here. So for example, looks to me like a B by itself is not in this language, right? And you can see that if you look at the DFA, right? If you just have a single B, not in the language. Or if you have just a BA, right? Not in the language. Or just AB, not in the language, right? Right? So the expression that represents this language, the regular expression that does represent the language shown in this DFA is this regular expression right here. Okay? It is not this. These strings are not in my language. So, question. What is the alphabet of this DFA? Are you sure? Pause the video. Think about it. So the answer is the alphabet for this DFA is going to be the set containing just two symbols, A, B, right? If I had the string, sorry, not the string, the regular expression that represented this DFA that we figured out on the previous slide, I can't tell you by looking at a regular expression what the alphabet is, because there's no guarantee. Maybe it's just that I don't use C's, but C's are in the alphabet. But in a DFA, because I know that I have to have an out transition for every letter of my alphabet, and since I told you this was a DFA, assuming this is a DFA, the alphabet must be just these two symbols. Okay? And here's a question. Are these both legal? So take a look. These are actually, let's say, are they both legal DFAs over the alphabet AB? Okay. So pause, think. So yeah, they are. You know, there's nothing wrong with me labeling a state as 23. It's unusual, but nothing wrong with it. And it looks like this first DFA recognizes all strings, right? It accepts all strings over the alphabet AB, anything that has any A's and B's in it, 0 or more. Because look, it even accepts lambda, right? Because if we start, as soon as we start, even if we don't see any symbols, we're in an accept state. So this accepts lambda. And over here, the second one accepts the empty set, right? No accept states, doesn't accept anything. But it's a legal DFA. And whoops, I answered this for you already, right? This is the same as the one before. Can you do it? Do you understand? Right? This is the language. A plus B, quantity starred. As many A's or B's as you want. All of them are accepted, even 0. Okay, we're computer scientists. We're also mathematicians. And so we like to be very, very precise in our language. So we're going to be a little bit more precise in our language about, no, we're going to be a lot more precise in our language about DFAs now. And just as a reminder, we call this a state transition. And we could describe this as a function, right? If I'm at state I, and I see the symbol A, right? So the transition starting at state I, if you see the symbol A, is you end up at state J. And as I say, we're going to use this capital T to stand for transition, or our transition function. Now, we could write each of these transitions out one by one, right? So we could say something like the transition, if I'm at state 0 and I see an A, that's 1. And the transition, if I'm at state 0 and I see a B, that's 2. But that gets very tiring very quickly. So we can put it into a table. Now this table is incomplete because every single state has to have a transition for every single symbol. So like we said, if we are at state 0 and we see an A, we end up at state 1, so that's what this number represents, right? We're at state 0, we see an A, we get 1. We're at state 0, we see a B, we get 2. We're at state 0, we see a B, we get 2. So let's look, what do we got to fill in? If we're at 1 and we see an A, we stay at 1. If we are at state 1 and we see a B, we also stay at 1. If we are at state 2 and we see a B, that's already filled in. We're at state 2. If we're at state 2 and we see a A, we also end up at state 2. Okay, so there's our full transition table. Pretty easy, right? Okay, so pause the video, do this by hand, and then, do it along with me. If I am at state 0 and I see an A, I get 1. If I'm at state 0 and I see a B, I get 3. If I'm at state 1 and I see an A, I end up at 2. If I'm at 1 and I see a B, I end up at 3. If I'm at 2 and I see an A, let's see, if I'm at 2 and I see an A, I go to 3. So 2 and an A is 3. If I'm at 2 and I see a B, I stay at 2. If I'm at 3 and I see an A, I stay at 3. If I'm at 3 and I see a B, I stay at 3. So these are going to be a 3 and a 3. And of course, by the way, I'm diagonalizing these, right? These numbers don't line up simply because I write too big and I can't fit them in the table if I try to line them up, right? There's nothing weird about this zigzag thing going on here. Or rather, perhaps I should say, it looks weird, the zigzag thing I have going on here, but in fact, pay no attention to it. So, next question. If all I know, if the only thing that I give you is this transition table, can you turn that into a DFA? And the answer is no, you can't. Because nobody says that the smallest numbered state is where you start. We never agreed to that. So you might not start at state 0 just because state 0 appears first in your transition table. And the other piece of information that we don't have in our transition function is which states are our accept states, right? So we don't know what our accept states are. So the transition function gives us a lot of information about a DFA, but not quite everything. So if we want to formally describe our DFA, we are going to give 5 different pieces of information. I'm going to tell you what's my transition table, right? I'm going to show you that transition table. I'm also going to tell you what are the names of all of my states. Now, you could figure that out from the transition table, right? Because if you look at your transition table, down the left column, you can see the names of all the states. But I'm going to tell you it again anyway. I'm also going to tell you what alphabet this DFA is over. Again, I could tell that if I looked at the transition table, but it's easier if I just tell you, here's what my alphabet is, right? What I don't know that I have to tell you is what's my start state, and I have to tell you my final states. And notice that my final states have to be represented as a set. Here's where we get nitpicky again, right? It's not just one final state. It might be 0. It might be as many as all my states. And similarly, the states are a set. Okay, so let's see how we formally write that out. And whoops, I forgot that I had a slide that said this. So just to be clear, yep, we could have figured these two out, but we're going to ask for it again. And yeah, just to remind you, exactly one start state. And like I said, 0 or 1 or 2 or 50, how, our maximum is just however many different states we have, final states. So here is a formal description of our DFA. We list the states first, and in this case our states are 0, 1, and 2. We tell you what's my alphabet. I say my transition function is T, and then I draw T off in the corner because it's too much of a pain to write it in lines here. I tell you my start state. It's just a singleton. It's always a singleton, so I just write it. No set state, no set symbols or anything. But my final states, my accept states, I always put in set brackets because there could be more than one. Now, because we like tuples, because when you are writing a proof, sometimes it's easier if you say, let's suppose we have a DFA formally described as a 5-tuple, and also because it fits better in textbooks if you can write things horizontally. We are going to describe our DFAs as a 5-tuple. Remember, a 5-tuple is a list. It's not a set, so the order of things matters. So you're just going to have to memorize this part, okay? We're going to have a 5-tuple, so we got the parentheses on the outside. Again, this is notation. You got to be nitpicky here. We have an open parentheses, right? And then after that, we list the states and the alphabet. Then our transition function, then our start state, and our set of final states. Okay. Now I kind of remember the order of the things in this five-tuple because I remember the transition table goes in the middle. The transition function goes in the middle. So for example, for this DFA that I have up here, here's my formal description. And you can see that I put my transition table, that's the third element of my five-tuple, right? And again, I said before, I'm just going to write a capital T here, and then off to the side, I'll show you my transition table. Okay. The things to the left of the T in the five-tuple are my states and my alphabet, so that kind of helps me remember the order. I have the states, then the alphabet. And on the right-hand side of the transition table in my five-tuple, I have my start state and my except states, my set of except states. And of course, start comes before except, so that's kind of how I remember the order of these things. Let's just look at this for a second and make sure it's correct. This says that for this particular DFA, my states are called 0, 1, and 2, and I look, and yeah, it's 0, 1, and 2. My alphabet is the set containing the symbols A and B. Yeah, that looks good. Transition table T, so if I'm at state 0 and I see an A, I'm at 1. If I'm at state 0, I see a B, I'm at 2, and so on. Yeah, this looks good. And my start state is, in fact, state 0. And my set of except states, there's only one. It is the state 1. So let's describe this DFA as a five-tuple, and just for this problem, I'm reminding you what order we need to give them in. Let's shrink this a little bit so we have, oops, a little bit more room. There we go. All right, so we're going to make a five-tuple. Five-tuple starts with parentheses, and we start with the states, which is a set, and in this case, I have the states 0, 1, 2, and 3, and I can put them in any order, right, because this is a set. So notice I started with the open parentheses because I have a five-tuple. The first element of my five-tuple is the set of states. Okay. Let's do a comma to show that we're going to the second element of my five-tuple now. Second element of the five-tuple is supposed to be the alphabet. This DFA is over the alphabet A, comma, B. The third element of my five-tuple is my transition table. I'm just going to write a big T for now, and we'll fill that in a minute. And the next element of my five-tuple is the start state. It's a single state, so no set symbols. And my start state is state 0. And then we want to know what is the set of final states. And again, in this one, we only have one, which is the state 2. And we close my five-tuple with a closed parentheses. Okay, so let's just shrink this a little bit so I have room for my transition table. And let's write that my transition table equals, let's see, we have 0, 1, 2, 3, and we have A, and we have B. So if we're at state 0, we see an A, we go to 1, 0, B, we go to 3. If we're at 1 and we see an A, we go to 2. If we're at 1 and we see a B, we go to 3. If we're at 2 and we see an A, we are at 3. If we're at 2, we see a B, we go to 2. And if we're at 3, and no matter what we see an A or a B, we end up at 3. Okay? So here is my formal five-tuple for this DFA, and it's this five-tuple, but this T transition table is an essential part of that because I just say, ooh, stuff T in here. Okay? And last slide, super challenge problem. Formally describe the regular expression A plus AB BA star as a five-tuple representing a DFA. Okay, let's stuff that up here. So the way we're going to do this, I mean, maybe you can do this from scratch, but I sure as heck can't. I need to draw the DFA and then turn that DFA into a five-tuple. So let's start by drawing the DFA, and then we'll figure out what the five-tuple looks like. Okay? So it accepts the string just an A by itself. So if we have our start state, and then we see an A, we accept that. We also accept if we see A, and then we see a B, and then we see another B. Well, we accept that, or if it has 0 or more A's after it. And there's definitely strings we don't accept. Oops. So let's just set up a trash state. So let's see if we're at 1. We're only accepting strings that start with an A, right? So if we have a B, we go down there. If we're at state 2 and we see an A, that invalidates it because it has to start with, it either has to just be an A or start with an A and then have a couple of B's before we see another A again. If we are at state 3 and we see an A, we go to our trash state. And if we're at state 4 and we see a B, we go to the trash state. So let's see if we can do our five-tuple for this, right? Well, let's just check first. We have a start, we have an A and a B. I'm just checking A and a B out for 1, A and a B out for 2, A and a B out for 3, A and a B out for 4, A and a B out for 5. We accept A, B, B, and then as many A's as we want. But anything else we go, yeah, this looks good. So let's do our, let's write our five-tuple. Let's do it in, say, purple, just so that makes things a little bit easier to distinguish. And maybe let's see, can I stick that there? Perfect. Okay, so let's see. Our five-tuple, oh, I told you I wasn't going to tell you this, but I did. Our five-tuple, we start with parentheses, and the first thing we do is we list our states, which is a set. So we have the states 1, 2, 3, 4, 5. The next element of the state of the five-tuple is the alphabet. And again, this is over the alphabet A, B. Then we have our transition table. We'll fill that in a minute. Then we have our start state, which is the state 1. And then we have our accept states, our final states, and in this case we do actually have more than one. State 2 is an accept state, and state 4 is an accept state. And the close parenthesis to close out the five-tuple. But we are not done until we show our transition function. 1, 2, 3, 4, 5, running out of space. And our alphabet is A, B. So if we are at 1 and we see an A, we go to 2. And if we are 1 and we see B, we go to 5. And 2A is 5, 2B is 3. 3A is 5, 3B is 4. 4A is 4. 4B is 5, and 5A and B go to 5. So there you go. That is our regular expression described as a five-tuple that represents the DFA. So really the purple is the answer to this question, right? The blue we just did to figure it out. Okay, I just wanted to give you a heads up that our approach to formally describing a DFA is a little bit different from the book's. The book basically does it a simpler way, but it's not as formal and not as common as the way we actually did it. So the book, instead of giving the formal five-tuple followed by the transition table, essentially just gives the transition table and then sort of fakes out where the start and final states are, in my opinion. They just kind of stuff it into the same table. Um, it does give all the information that we give to, but I wanted to teach you this approach because you will see a lot of people using this more formal approach where we actually describe things as a five-tuple. So for the purposes of our class, we're going to continue to use the five-tuple. But if you happen to be reading the book in a later portion in this chapter, it's going to tell you about these transition tables, and it's going to describe them this way.